Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we'll be looking at how you solve second-order differential equations that have variable coefficients by using a substitution. But first of all, we'll remind ourselves about first-order differential equations that require a substitution. First order, because we only have dy by dx in the equation. If it had d2y by dx squared, then it would be a second-order equation. We need to substitute y into the equation. We also need to substitute dy by dx into the equation, and that we'll have to calculate. So using the product rule and differentiating both sides with respect to x will give us dy by dx is equal to u plus x du by dx. Substituting this and y into the differential equation will give us this. Multiplying out the brackets and collecting together terms will give us this. Dividing through by x squared will give us this. And then we can solve this by separating the variables. So the integral of 1 over 4 plus u squared du is equal to the integral of 1 over x dx. Now the left-hand integral is a standard integral. It's very, very close to tan to the minus 1. It's slightly easier to see if you take the quarter outside of the integration, so that you have a quarter into the integral of 1 over 1 plus u over 2 squared du equals the integral of 1 over x dx. And then this is a standard integral for inverse tan of u over 2. And if we were to differentiate that, when you differentiate the inverse tan, you get 1 over 1 plus u over 2 squared. And when you differentiate the u over 2 using the chain rule, you'd be timesing by a half. And a half times the half gives us the quarter. The right-hand side is a great deal more straightforward. The integral of 1 over x is log x plus the arbitrary constant. And then the next thing we need to do is undo the substitution. So the substitution was that y equals ux. When we write down the general solution, we really should be writing down y as some function of x. If y equals ux, that means u equals y over x, and that we substitute back into here. So that gives us a half inverse tan of y over 2x is equal to log x plus c. Multiplying by 2 will give us that. And then if we take the tangent of both sides, then tangent and inverse tangent cancel out on the left-hand side, leaving us with y over 2x. And on the right-hand side, we get tan 2 into log x plus c. And finally, moving the 2x to the other side gives us the general solution, that y equals 2x times by the tangent of 2 into log x plus c. Okay, example 2 is a lot more difficult. It's a second-order differential equation with variable coefficients. We've got x squared here and minus 2x here. And we're going to solve it by using the substitution x equals e to the u. Now, we've been told x equals e to the u, but we have to calculate dy by dx. We have to calculate d2y by dx squared. And both of those are quite tricky. Once we found x dy by dx and d2y by dx squared, we substitute them into the original equation, and the equation will transform into a second-order differential equation with constant coefficients that we are able to solve by normal means. Now, as I say, it's quite tricky, but have a go yourself, pause the video, and come back to me again when you're ready. Okay, let's have a look at this. So we begin with the substitution, x equals e to the u. If I differentiate both sides with respect to u, I'll get dx by du is equal to e to the u. That means du by dx is 1 over e to the u. And then using the chain rule, dy by dx, which is what I want, is equal to dy by du times by du by dx, which is dy by du times 1 over e to the u. That was what I just found. It's a little bit easier on this question if we choose to write that as e to the minus u dy by du. So we've been given x, we've worked out dy by dx. Now we need to work out d2y by dx squared, which means we need to differentiate both sides of this equation with respect to x. On the left-hand side, we'll get d2y by dx squared, and the right-hand side will differentiate using the product rule, writing down the e to the minus u, differentiating dy by du with respect to x gives us that. Then writing dy by du and differentiating e to the minus u gives us that. And using the chain rule, when we differentiate the minus u, we'll get minus du by dx. Now, the next thing is the really tricky bit. You may not have seen this before. It's the chain rule for second differentials. And if you don't know it already, you should learn it. D by dx of dy by du is equal to d2y by du squared times by du by dx. So that's the chain rule for second differentials. It looks vaguely sensible if you were to treat these as fractions, which obviously they're not. And if you cancel the du from the top and the bottom here on the right, what you would get would essentially be what you have on the left. Some people think it's obviously true. I never think it's that obvious myself. Anyway, it's this term here that we'll need to substitute in with d2y by du squared times by du by dx, which will give us that. Du by dx is the next issue. Now dx by du, so if we differentiate x with respect to u, we'll just get e to the u, which means that du by dx is 1 over e to the u, or e to the power of minus u. So substituting in for du by dx here and here, and multiplying the e to the minus u's together, will give us d2y by dx squared is equal to e to the minus 2u times by d2y by du squared minus e to the minus 2u times by dy by du. We've now worked out all three things that we needed to work out, and we can substitute those into the differential equation. When we do that, this is what you get. Now it looks extremely complicated, but it does simplify very quickly. E to the 2u times by e to the minus 2u is e to the 0. E to the 0 is 1. And that happens several times. So the whole thing simplifies very quickly into that. These two middle terms we can add together, and that gives us d2y by du squared minus 3dy by du minus 10y is equal to 0. So we started off with a second order differential equation with variable coefficients that we were not able to solve. By using the substitution x equals e to the u, we've been able to transform it into a second order differential equation with constant coefficients that we can solve by the normal method. So the auxiliary equation will be n squared minus 3n minus 10 equals 0, which factorizes into n minus 5 times n plus 2 is 0, with two solutions, n is 5 and n is minus 2. Now, if the auxiliary equation has got two distinct real roots, then this is the general form of the complementary function, which means in this particular case, the complementary function will be ae to the 5u plus be to the minus 2u. We now need to undo the substitution, x equals e to the u. If x equals e to the u, we take logs of both sides. So that'll give us log of x on the left-hand side, and then log of e to the u. The log and the e are inverse functions. They cancel each other out, and that is just u. So u equals log x. We substitute that into here and here, which will give us a complementary function, ae to the 5 log x plus be to the minus 2 log x. Now, this next stage is quite important. It turns up frequently on these questions, and it does just help you simplify things. ae to the 5 log x, the 5 can become the power using the rule 4 powers, so that becomes ae to the log x to the 5, and same thing with the minus 2 here. That becomes be log x to the minus 2. Having done that, the e and the log can then cancel each other out because they're inverse functions. So that gives you a complementary function of ax to the 5 plus bx to the minus 2. Now, in this question, there is no function on the right-hand side, so there is no particular integral defined, and there are no boundary conditions. So the general solution is y equals ax to the 5 plus b over x squared. Now, example 3 is a slightly different type of question. Again, you have a second order differential equation. This time you'll notice that the substitution is dy by dx is equal to u. Now, when we substitute that into here, what we will get is a first order differential equation. We solve that first order differential equation in the normal way, and when we do so, we find that the solution is itself a first-order differential equation. So we then solve that first-order differential equation in the normal way and get the general solution. In this case, there'll be boundary conditions, so we'll be finding a particular solution at the end. Anyway, have a go at doing all that yourself. Pause the video and come back to me when you're ready. Okay, let's have a look at this. So that's what we've been told. The substitution is dy by dx equals u. We need to differentiate both sides with respect to x, and that'll give us d2y by dx squared equals du by dx. But this time, it's very easy. We found dy by dx, we found d2y by dx squared. We can substitute both of those into the differential equation immediately. And that will give us du by dx plus 2 over x times by u equals 0. Rearranging that gives us du by dx equals minus 2u over x. And that we can solve by separating the variables. So we'll get the integral of 1 over u is the integral of minus 2 over x. Integral of 1 over u is log u. The integral of minus 2 over x is minus 2 log x. If we then take e to the power of both sides, same reason as in the last question, the e and the log here will cancel. But on the right-hand side, we need to do a little bit of work first. If we split that up into two parts, on the right-hand side, we'll get e to the c times by e to the minus 2 log x. Now, on the left-hand side, the e and the log will cancel, so we have just got u. On the right-hand side, the power, or the minus 2, goes up and becomes a power, like on the previous question. So we'll get e log x to the power of minus 2. Then the e and the log can cancel each other out. And here, where we've got e to the power of c, e and c are both constants. The normal thing is just to join those together in one other constant. So u equals a, and then we've got x to the power of minus 2. The only reason for doing that change with the e to the c and a is it just looks neater. It does look a bit more tidy. So u equals a x to the minus 2. Now, that still has u in it. The original equation didn't. We need to undo the substitution, which was dy by dx is equal to u. We can literally just substitute straight in there. And that gives us dy by dx equals ax to the minus 2. So we solved a first order differential equation. And when we solved it, this is what we got as the solution. Another first order differential equation. We now solve this equation in the normal way. So integrating both sides with respect to x will give us y equals minus a x to the minus 1 plus b. Therefore, the general solution of this equation is y equals minus a over x plus b. But this time we can find a particular solution. We've been told y equals 0 and x equals 1. Substituting those in here gives us 0 equals minus a plus b. The second boundary condition is slightly more complicated. We're told that y tends to 1 as x tends towards infinity. Now this is y, so it means that this minus a over x plus b tends towards 1 as x tends towards infinity. But as x tends towards infinity, this first term will tend towards 0, because minus a over infinity would equal 0, which means that b must equal 1. Once you found b equals 1, you can go back to this equation here and find out that a also equals 1, which means that the particular solution is y equals minus 1 over x plus 1. Okay, example 4, and this really is the nightmare scenario. You have a second order differential equation, a bit like we had in example 2. We'll be using the substitution x equals e to the t. We'll have to work out dy by dx as we did before. We'll have to work out d2y by dx squared as we did before. Once we've done that, we'll substitute those into the equation. Then the equation will transform into a second order differential equation that we can solve. There will be a particular integral that you have to find. And at the end of all of that, there will also be these boundary conditions that you need to substitute in order to find the particular solution. So have a go at this yourself. Good luck. pause the video and come back to me when you're ready. Okay, let's have a look at all of this. So we begin with x equals e to the t, which I've done in blue just because I want to keep track of the three things I need to substitute into here. Then differentiating with respect to t gives me dx by dt is equal to e to the t. Using the chain rule, dy by dx is dy by dt times by dt by dx, which is the same thing as dy by dt times by 1 over dx by dt, which I calculated back here. So dy by dx is equal to dy by dt times by 1 over e to the t, which as in example 2, it's just slightly easier if I choose to write that as e to the minus t times by dy by dt. So we were given x, we worked out dy by dx, now we need to work out d2y by dx squared, which means that we differentiate both sides with respect to t. On the left-hand side, I'll get d2y by dx squared, and the right-hand side, I'll have to use the product rule. So we get d2y by dx squared, writing down the e to the minus t is that. Differentiating dy by dt with respect to x gives me that. Then write down the dy by dt, and then differentiate e to the minus t with respect to x, which gives me e to the minus t. And then when I differentiate the minus t with respect to x, I get the minus dt by dx. Then we have to use the chain rule for second differentials, which is this, which means I substitute in here d2y by dt squared times by dt by dx, which gives me that. Then we need to worry about the dt by dx. Well, dt by dx is 1 over dx by dt, and dx by dt is e to the t. So substituting that in will give me that. And then these two terms I can join together to get e to the minus 2t, and same again here. So d2y by dx squared is equal to e to the minus 2t times by d2y dt squared minus e to the minus 2t dy by dt. Finally, we've done all of the work that we need to do to transform this differential equation. So now we can substitute in those three expressions. And substituting those in will give us this. I'm doing a little bit of tidying up with these e to the t's, gives me that. These two terms in the middle cancel with each other, so it simplifies to this. Then factorizing will give me that. And then moving e to the minus 2t to the other side will give me d2y by dt squared plus y equals 5e to the 2t. So we started off with a second order differential equation with variable coefficients that we were not able to solve. By using the substitution x equals e to the t, we've transformed that into a second order differential equation with constant coefficients. Now there's no dy by dt term, but that's not a problem. We can still solve that by the normal method. The auxiliary equation will be n squared plus 1 equals 0, which gives us two complex roots, plus or minus I. Now with complex roots, the complementary function has this general form, which in our particular case will give us a complementary function of e to the 0x times by a cos 1t plus b sine 1t. Anything sparrow 0 is 1, so the complementary function simplifies to that. Now in this instance, we do have a function on the right-hand side of the differential equation, 5e to the 2t. The general form of that is ae to the 2t. So the particular integral will be y equals ae to the 2t. Differentiating that with respect to t gives us that. Differentiating that with respect to t gives us that. We can now substitute back into this differential equation here. And when we do so, we will get that. Adding those together gives us 5a e to the 2t is 5e to the 2t, which means 5a equals 5, which means that a is equal to 1. We now know the particular integral. The particular integral will be yp equals 1 e to the 2t. And the general solution will be the complementary function plus the particular integral, which gives us that, a cos t plus b sine t plus e to the 2t. Now, as is always the case, when you do a substitution, at the very end, you're going to have to undo that substitution. So that is the general solution of the transformed differential equation, but we need to undo this substitution in t and return it to x's and y's. The substitution was x equals e to the t. So undoing that, if I take logs of both sides, that'll give me log x is equal to the log of e to the t. Log and e cancel with each other, and that will give me t is equal to log x. And I can substitute for t in the solution to the differential equation here. And that will give me y equals a cos log x plus b sine log x plus e to the power of 2 log x. This final term here, using the rule for powers again, that can be changed to e to the log x all squared. Then the e and the log can cancel with each other. And that'll give me the general solution of the original differential equation, y equals a cos log x plus b sine log x plus x squared. Now, we were given boundary conditions in this question. The first one was that when y is 3, x equals 1, substituting those into the general solution will give me 3 equals a cos log 1 plus b sine log 1 plus 1 squared. The log of 1 is 0, so that'll give me a cos 0 plus b sine 0, moving the 1 over to this side gives me 2. The cosine of 0 is 1, the sine of 0 is 0, so that simplifies to a equals 2. Now the other boundary condition tells me what dy by dx is when x equals 1, so I'll need to differentiate the general solution to get dy by dx. And when I differentiate this, I get a sine log x times by 1 over x using the chain rule, plus b cos log x times by 1 over x, also using the chain rule, plus 2x when I differentiate the x squared. That tidies up to give me minus a over x times sine log x plus b over x cos log x plus 2x. And then I can substitute in the second boundary condition, which is dy by dx equals 3 when x equals 1, also substituting in a equals 2 here. And that'll give me 3 equals minus 2 sine 0 plus p cos 0 plus 2, which means that b is equal to 1. And finally, we arrive at the particular solution of this differential equation, which is y equals 2 cos log x plus sine log x plus x squared. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 120 and have a go at exercise 6D. Thank you very much for listening, and cheerio.